Okay, so today for the grad student session, I'm going to go over the auditory thalamus and cortex. So we rightfully spent a little more time on the brainstem in the auditory system because there's so much going on down there. And but there's a cortex and a thalamus, and so we'll go through kind of the equivalent of there's the lateral geniculate and the medial geniculate, which the medial geniculate is for the auditory system. So we'll go over that and then just go over the layout of the areas in cortex and some of the higher level projections that branch off of the primary auditory cortex. And then I'll talk about pitch. So pitch versus frequency. And this gives us some insight into kind of what goes on in the auditory system. And to do that, we have to talk a little bit about what typical sounds are actually like. And so we'll go over that in the second, last third or so, second half. Okay, so let's. So what we already did. So we had. Let me just draw sort of a quick and dirty diagram down here. So we had, the pons midbrain junction there. And so the nuclei that we already talked about, we have the cochlea, hair cell comes in, there's a hair cell, there's a hairs. It comes in and it branches, and there's three nuclei up here. So here's the midline. And they each get a projection from, it's not in the nucleus. There we go. So they each get a projection from a single cochlear ganglion cell. And then if we're talking about a mammal, we've got there's the lateral superior olive, which kind of looks like an S, and then the medial superior olive, and then there's some olives, peri-olivary nuclei that are on top of each other. And then here's the trapezoid body. There's the medial nucleus of the trapezoid body. So there's a whole. So these guys generally, project down there, mostly on the same side. There's some crossing, at the level of the trapezoid body, and then there's some nuclei of the lateral meniscus up here. There's three of those guys. Nuclei of the lateral meniscus. So this is, gotta get different label colors. Okay, so there's the nuclei of the lateral meniscus. This guy is the lateral superior olive. This guy is the medial superior olive. Medial superior olive. And these are peri-olivary. And don't forget the medial nucleus of the trapezoid body. Peri-ol. And then when we get up to the midbrain, we'll talk in the main lecture. We'll talk about what's going on in the inferior colliculus. So you got the inferior colliculus, and there's external nucleus, and a couple other nuclei around it. And then we go up to the medial geniculate nucleus. So the medial geniculate nucleus it has several parts to it. And then eventually we get up to the cortex. So here's the cortex, auditory cortex. And if you just look at the overall sort of structure of these projections, basically the way it looks, it generally follows the rule of Serino. So you have, these guys are on the same side. There's a little bit of crossing having to do with binaural, which we talk about. And then this goes up to the midbrain structures, mostly crossed, and then the midbrain projects to the medial geniculate, mostly uncrossed, all uncrossed, and then there's a projection up to the cortex. So So here's, odd cortex. This is medial geniculate nucleus. So medial nuke. And this is the inferior colliculus here. So that's what we already did down here. And so let's look at the medial geniculate and the cortex. So if we start off in auditory thalamus, so auditory thalamus, what does that look like? So if you remember back in the day, seems like such a long time ago, when we were talking about the development of the thalamus, it kind of starts off as four little bumps on the neural tube. And the top bump forms the epithalamus, the habenula that's hooked up to the pineal. And then there's the second from the top bump, which forms the dorsal thalamus. The dorsal thalamus was the biggest one. And so why geniculate? So genu is a knee. And so it's the second knee. It's the medial knee. So if you look at the human brain, pull out a human brain, you can see two little very clear bumps in the thalamus. This is, if you just look at it from the outside, and one, the more lateral one is the lateral geniculate, which we already talked about, and then the medial geniculate is the, and so it actually sort of sticks out a little bit like that from the brainstem. And then, so here's the midline going down. So remember, there's the ventral thalamus. So the ventral thalamus, it kind of goes around, around the thalamus. That was a bunch of obscure nuclei you probably haven't heard of, like, the zona incerta. And then there was the hypothalamus. So here's, so there's the other side, same thing on the other side. So, so this is the dorsal thalamus, of which the medial geniculate is part. So that's dorsal thalamus, epithalamus. This is ventral. Let me get that out of there. Ventral and hypo, drug, sex, and rock and roll. And so the medial geniculate is kind of sitting here. It's a big chunky thing, and it's got, we'll put, there's various subdivisions, but it's got a really big one down slightly at the bottom. So we'll put four subdivisions in there. And so the first one is this guy, and that's the medial geniculate principal nucleus. And that's the biggest. That's the biggest one. It has the finest grained tonotopic map. And then you've got two higher level geniculate nuclei. And so remember, in the visual system we had the lateral geniculate nucleus, but then there was this other thing called the pulvinar, which is in the visual system is actually, because the visual system is so big, it's actually bigger. It's like about 5 times bigger than the geniculate, and that the pulvinar receives input from V1 and other areas, receives ascending input, and then that goes to some of the higher visual areas. You got the same thing in the auditory system. So this is the medial geniculate dorsal anterior, and this guy is the medial geniculate dorsal posterior. So dorsal posterior, and this guy is dorsal anterior. Okay, so those are that's the kind of layout there, and then there's a fourth one. This one's called the MGM, and that's the magnocellular medial geniculate. geniculate medial. Medial geniculate. And this guy, out of all of these structures, this guy is the only one that appears to be non-tonotopic. It doesn't mean it doesn't care about different frequencies. And in fact, if you train an animal to pay attention to a particular frequency, you can, and then test the sensitivity to frequencies there, you can see that it's actually modulated. But in general, there's no obvious map where different frequencies are mapped. All these other guys, virtually all these other guys are mapped. These guys are certainly mapped. All the superior olives are. The nucleus of the lateral lemnisci, the inferior colliculus, except for the external nucleus, which we'll see in the main lecture, and then most of the things here. So almost everybody's mapped. And when you go up into the cortex, the maps continue. So when the naming up there is, a little bit of a mess because people have slowly figured out more subdivisions as time went on. And so, back in the day there was S1 and S2. They thought there were just sort of two, and then they made V1 and V2, and then there was A1 and A2. So A2 is kind of slightly gone by the wayside, sort of been superseded by a bunch of areas. So there's a reasonable number of areas there. I just wrote a paper on sort of parcellating all the different visual, auditory, somatosensory areas. If you go to my homepage, you can find it if you want to see. But how many did I put? 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Maybe about 20 or so. So we're not going to go through all of them, but we'll just sort of try to point out approximately where they are. So if we draw left hemisphere here, basically and then this thing is the superior temporal sulcus. That's kind of a landmark. So this guy was the lateral sulcus, sometimes called the sylvian. And this guy was STS for superior temporal sulcus, because there's kind of an inferior temporal sulcus, but it's not a very good sulcus. It's kind of little dense over there. So the superior temporal sulcus is the main one. It's a deep, very deep sulcus. And so where's the auditory system? Well, it pretty much covers the upper part of the anterior part of the the temporal lobe, and it goes down into the superior temporal sulcus a little bit. So here's like a cutoff arrow down in there. Sorry about that. And then it comes back up, and there's a little collection up there, and then a lot of it goes into the. Here's another cutoff arrow. Goes into the lateral sulcus, and so this is our auditory areas. Like I said, it's about 1/8 in a macaque monkey. It's about 1/8 of the cortex, compared to like about a half of the cortex for visual. And if we draw like a side view, sort of a transverse section. So if we cut down through here, what you have is you have the insula, and then here, let's put it like this. So it comes. So if you look in the lateral sulcus, you've got this something like that, and then eventually we get into the superior temporal sulcus here. So this is the superior temporal sulcus. So this is lateral. This guy is STS. And the visual stuff, starts down here. So this guy is visual. And then the auditory stuff, some of it, goes up a little bit, into the insula, but it mostly sort of sits something like that. So that's auditory. auditory, and that thing is called the superior temporal gyrus. STG, yeah, gyrus. So this guy, yeah, this gyrus here. Now, if you actually look, it doesn't look flat like that. So if you actually kind of peel open the temporal lobe and look at the top of the temporal lobe, it's actually not flat. There's a gyrus there right where primary auditory cortex is. And so if we sort of peer in there, what does it look like if we sort of pull it out? It looks like there's actually sort of like a very clear, almost sort of mushroom-shaped, gyrus in there like that. And so this is the this thing here corresponds to that. And so if you keep going in, you'll get into the insula. But this is before you got into the insula. So here's the superior temporal gyrus right here. And so this is inside lateral sulcus. And so that thing, that little bump in there, and people vary. Some people have two bumps in there. So that little bump in there is called, so that's the cortex in the bump. That's called Heschel's gyrus. So that little ridge in there, and that's pretty much right where primary auditory cortex is. So this is Heschel's gyrus. And like I said, if you look on an MRI at a human, a lot of times people have a double Heschel's gyrus. So maybe 30 or 40% of the people have two little Heschel's gyri instead of one. So I don't know if that makes you a better person, but you just see a variation in how many you have. And it's very myelinated there, and that sort of goes along with the general picture that the earlier stages are doing more work. And so the overall picture here is we've got all this really high performance hardware down here to do some of our initial digitization of the signal, and then things get lazier as you go up. But if you go on the cortex, the most myelinated area is primary auditory cortex. And so if we just kind of stretch the whole thing out and look at it flat, so we'll go from like somewhere down, entering into the superior temporal sulcus, and then get all the cortex that's on the inside the lateral sulcus, that corresponds to this right here, sort of stretch the whole thing out. Our overall picture, looks something like this. So what happened was, with primary auditory cortex, people sort of like poked around, literally, and tried to sort of figure out how it's laid out. And they first figured out in cats that what they thought was primary auditory cortex actually had at least two parts. And in primates, they think it has three parts from connections and mapping. And so what those three parts are is you got primary auditory cortex on Heschel's gyrus. So that would be kind of sitting right here. There it is. It's primary auditory cortex. And then there's another slightly smaller but still pretty myelinated area. And that initially was sort of following up on the cat work. And then there's yet another one. And so these, and they're all kind of myelinated. They'll have a lot of cytochrome oxidase, kind of hard-working areas. So this guy is A1. They write it various ways, sometimes A Roman numeral 1, sometimes just A1, sort of just the number 1. And this guy was called R, and what's R is rostral. And so so there's several, so you can, if you aim toward the nose, that's kind of rostral, whereas caudal is aiming toward the tail. But you can also call that anterior. But in the auditory system, they use this sort of rostral and caudal. And then this guy is the rostral lateral area, because it's it's coming out of the lateral sulcus there. So everybody agrees more or less on these, and then just like anything else, there's more dispute. And so there's some areas that are sort of medial, and these guys, there's several divisions there, 2 or 3 divisions there, and this is called, they have different names, but I won't write them down, but in general this is called the medial belt areas, sort of like V2. And then there's another set of areas around here called the, there's at least, so I'll stick, I put in 4 in my parcellation. So this is the lateral belt, also like V2. And then there's some dispute exactly what goes on. There's some areas, right behind it. We don't know how many there are in there, but there's a couple in there. Maybe that's part of the lateral belt. And then we have what's called the parabelt. There's other names for it, but we'll call this guy the parabelt. So that's like V3. The third sort of row of areas. And then as you go further forward down onto the front of the temporal lobe, there's at least 2 additional areas there. And most of these have some sort of mapping of frequency. So if we just sort of go into A1, approximately, where is the high and low? So the high would be on this side, and the low would be on that side. And there's still tonotopy when you get out here. So this is low at this end and high at this end. And these guys have disputed names. Some people call them like TA123, and other people call them TS123 going the opposite direction. We'll just call it TA2 for temporal lobe area A, number 2, TA3. And as you get down into, there's some multimodal areas down here. So there's some auditory input that continues. So this is multisensory areas. They've got auditory and maybe some visual or even some metasensory input in them. And what if we go sort of further into the hinterlands? There's actually, I need a different color for that. So there's actually some visual areas that sort of tuck in right here, very close. And there's some other visual areas out here. And if you keep going, you'll eventually get back to MT. So here's MT. Remember, MT was, and so this guy here it's got various names. Sometimes people call it 7B, but you could also call it posterior insular cortex. It's actually kind of tucked in. It would be right sort of tucked inside there. You can't see it from the outside. But that one's got a visual and some metasensory and auditory stuff. So you can see it gets quite close to primary auditory cortex. There's some visual stuff quite close to primary auditory cortex. And there's some sort of hinterland things in the insula here, additional areas. There's an area called, insular granular cortex. Let's say insular granular cortex, little area in there. And then you're immediately on to somatosensory cortex. So this is somato. This guy is visual. So that's kind of our, and as you Sometimes there's a little bit of auditory stuff on the other side of the visual. It's complicated. This is a very complicated area, right in this region here. There's a lot of areas all sort of crammed in there. It's often activated in various kinds of fMRI experiments. So what people have done in the auditory system, sort of similar to the visual system. So if you look in the visual system, there's this general idea that you have streams that we talked about at the beginning, like say X and Y streams, but as you go higher up in the visual system, there's a general tendency for areas that are more in parietal to be concerned with the location of things, or particularly coordinating visual information with manipulation, like with your hands and feet and mouth and stuff like that. So those areas up there, have been called the visual, where pathway or how pathway, sort of like messing with things. So this is visual where and how. And when you go down this way, there's more streams than this, but this was like an initial distinction by Ungerleider and Mishkin, that you have, this is the what pathway that is more involved in recognizing what the object actually is. These things are massively interconnected, and so again, people they would like to sort of separate out the functions, but you can find sensitivity to object shape up in the parietal cortex, of course. I mean, if you want to grab something, you have to sort of know what its shape is, like what's the orientation. That's kind of something that normally people associate with the what pathway. So this was the visual what. And so the idea is you got like sort of a something like that and something like that that are coming out of early. So here's early visual areas back here, and then you've got this what versus where. So object recognition versus spatial attention, paying attention to where stuff is, using it to sort of direct action more. So people have made a similar distinction in the auditory system. And the distinction in the auditory system is that, as you go forward, that's kind of more like the what pathway. And as you go backward, so this guy is, auditory what. So when we talk about, so people have suggested that there's areas that are particularly involved with determining pitch. We'll talk about, pitch. What is pitch? As you go down the front of the temporal lobe, and then as you go back toward the visual where-how pathway, this guy is the auditory where-how. That's quotes on that, overlapping. Auditory where-how. As you head up into the back of the posterior insular cortex. And there's other stuff in there. There's vestibular cortex in there, because the vestibular system, that's involved in sort of head rotation and translation and rotation of the head. That's basically an auditory structure that actually receives input from the same nerve that the auditory, all the straight auditory stuff is coming in from. And so that's kind of like the basic layout of the. And so once you get here, we're back into visual. And there's a lot of, like right in this region here, in the superior temporal sulcus, in between the auditory and the visual system, there's a lot of good language stuff. If you're sort of interested in languagey functions, there's a lot of sort of languagey stuff here at the boundary between visual cortex and higher level. So higher level visual cortex and higher level auditory cortex. Okay, so I think that's a pretty good overall picture of higher level auditory system. Now, we mentioned that, if you look at the auditory system, we've got these isofrequency lines, going across auditory cortex, because we have, point to plane type projections, only one dimension of the cochlea. And so, one question is that people have had is, what's perpendicular to frequency? And when we talked about the down in the brainstem, when we talked about the nucleus laminaris, which is like medial superior olive, we said we have characteristic delay, which we'll try to explain even better in the main lecture, that was perpendicular to, so let's write that, what is perpendicular to frequency? So over the years, people have come up with various things. So one obvious thing that could be perpendicular to frequency might be, say, amplitude. That was an early suggestion from Auditory in the dog brain. So amplitude, is that there's been some suggestion maybe that's what's perpendicular. Space could be perpendicular, and that's actually what more or less is perpendicular when we talk about the nucleus laminaris. What's going the other way from frequency? It's basically it's characteristic delay, which corresponds to, like, we'll see it corresponds more or less to where you are on the horizontal axis. So, space is another possibility people have suggested. Another suggestion is periodicity. And periodicity is, periodicity just means sort of like, repeating something that repeats. Now, isn't a sound wave repeating? Yes, so sound wave is definitely repeating, but there's some suggestion that there's mapping of things like, like tap, 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 about that speed, or a little bit faster. Tap, 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 tap. So there's some suggestion that different, very low frequencies like that are mapped perpendicular to these much higher frequencies, like 500 or 1,000 hertz. Now, it's also known that if you actually look perpendicular to frequency, you see inhibitory excitatory zones. Inhibitory excitatory binaural. So that the question is, if you stimulate the other ear, what happens? Are you excited, or so it's very clear there are these little bands that are perpendicular to frequency. So there's kind of a lot of different things. We don't actually know. We'll talk in much more detail about the brainstem, where we do know, where there's definitely, we know for sure that there's at least space. And one of the things to sort of keep in mind, which I mentioned before, is that auditory cortex, because there's so much stuff going on in the brainstem, auditory cortex is kind of at a higher level. And this one, I like this one experiment. I'm talking about this one obscure experiment. Probably nobody ever talks about it in any other class. But if you go into auditory cortex, and if you play the following thing, let me make a little space for myself here. So if you play just a series of pitches, and then look at the response of a cell. It's going to be tonotopic, so it will, respond. So if here's my stimulus, so I just play a bunch of pitches like that slowly go up. So that's frequency going that way, and this is time going that way. And then look at the response. So this is This is stim and response. Now this was done in, I think it was an anesthetized cat or monkey, so it's not even a conscious animal. And if you play that, and what does that sound like? It would be something like, just like a whole series of little pitches. What happens is you'll see that the cell, if the cell is tuned to this frequency, you'll see like a little, a spike in response that will be biggest for that frequency. That's the center frequency of the cell. And then as you go up, the responses will tail off. So it's tonotopic. That's what we mean by tonotopic. So you have to get the correct frequency, whatever that frequency is. So at this time, we just happen to hit the right frequency. So, tuned. So this cell, cell tuned to this frequency. Now, this is primary auditory cortex, kind of like primary, visual cortex. So they did this experiment where they just left out the center tone. So basically, you just play the tones until you get to the center tone, leave it out, and then just continue on. So this is the stimulus response. Here's another stimulus and response. And what's plotted here is just the frequency again. So this is, frequency going up here like that. And so what does that sound like? That just sounds like, Now this is primary auditory cortex, and what you see in the response is it just responds to that missing tone. So it goes, and then there's a missing tone. There's a good response there to nothing, and then it starts to fall off again when you get the real tones. So this is, response to nothing in an anesthetized animal, because it was kind of expecting something to be there. So something like this wouldn't happen, much less likely to happen in primary visual cortex. It would more report what's actually going on. So that's an experiment, suggesting that visual, auditory, primary cortex, higher level already. Higher level than visual primary. So, okay, so there's still a few minutes left. So this is, there's a zillion experiments in higher level auditory cortex, which I haven't talked about here, which you can go and read, but this gives you some idea of what the layout of these areas are. So the primary areas, medial lateral belt, parabelt, some multisensory areas, higher level areas as you go down the temporal lobe, some higher level areas as you go back here as you come out of the back of the lateral sulcus. So that's kind of where and how, and this is more like what kind of a auditory object is it. Okay, so let's talk about pitch. And so when we talk about pitch, I'll erase everything. So you might think like pitch and frequency sort of sound like the same thing. And what do we mean when we say pitch? We mean like if I just do that sounds like a particular note, like a note on the piano or a note on a flute or something like that. So that's the pitch. So why do we obviously that's a higher pitch. and it's obviously got some higher frequencies in it. And so what's the difference between pitch and frequency? Aren't they kind of the same thing? They're certainly arranged in the same order. So higher pitches contain higher frequencies. But it turns out that you actually don't have a straightforward mapping at all. And this was figured out a long time ago. It was figured out in the 19th century by enterprising British and German psychophysicists like Helmholtz. So it's really interesting to go back and just get Helmholtz out from the library. I know I haven't been to the library in years, but and just see what he's up to. So so how did they figure this out back then? Well, they had a lot of tuning forks, but they also, I always make this drawing, they had mechanical oscilloscopes. And so, because there's quite high frequency, so here's some sound waves, that's quite high frequency. So how did they do this? Well, they got a horn and then focused that horn down to a little tiny mirror. So hanging from like a hair. It's a little tiny mirror. And then they had a big light source over here, which they reflected off that mirror. And then they reflected it onto a very rapidly moving piece of unexposed film. This thing was called a phonodike. And so basically, you load up a spring-loaded piece of unexposed film and then let the spring go, and the film whips by like that, and what happens is the mirror, which is hanging by this little hair, gets vibrated by the sound, and it makes a sound wave on the film. It was hard work. I had to walk 10 miles to school. Now we just have an oscilloscope. You just plug it in, and you can get that very easily. But this is how they actually figured this out originally. And so it turns out if you actually look at physical objects, any kind of physical object, and the simple example would be like a guitar string. If you pluck a guitar string, the string will tend to, so here's the guitar string attached here and here. So one of the things the guitar string can do is it can sort of move in this kind of way. So it will sort of bow out and then bow out the other way. And it will go back and forth rapidly. Depends how fast it goes, depends on how heavy the string is, how much tension you got on the string, but this is the kind of thing that can happen with a guitar string. But it turns out there's other kind of things that can happen with a guitar string. And so this guy is called the first harmonic. Now, the other things that happen with a guitar string, they're quantized, kind of like quantum mechanics. So the second thing that happens with a guitar string is it could vibrate. Say you plucked it right over here. Then what's going to happen is the guitar string is going to vibrate like this. And this is called a standing wave because it's not moving. We can sort of, mathematically you can sort of think of it as two moving waves are going in opposite directions, but we'll just leave that out. So the guitar string, just think of it physically like the guitar string could just sort of go like wah, 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 wah. But it doesn't ever go like 1.5. It does 1 and then 2, and then the next one will be 3. It's quantized. And what does 3 look like? And there's 3 of them there, so the guitar string could do that. And then here's the opposite one. So that's the third harmonic. Third harmonic. And this kind of structure applies to all different kinds of objects, like your vocal cords. Your vocal cords are a little vibrating device. It has like a whole bunch of harmonics, like 30 harmonics that are coming off your vocal cords. Now, what are the frequencies of these harmonics? So this guy, at frequency, let's say, for example, is 100. So it's going back and forth. Say, let's do it. Let's make it like the bass note of a guitar is about 80. So 80 hertz. That's the E string. Low E guitar. Okay, so that's 80 hertz, and then what's the second harmonic? It's 160 hertz. It's just 80 times 2. And what's the third harmonic? It's just 80 times 3. So that's 240 hertz. So that's, 80 times 3, 80 times 2. And it goes way up. It goes up to like the 10th or the 20th harmonic. So, et cetera, to 10, 20 harmonics. Now, it turns out everything is, almost all physical objects are like that. Any kind of physical object, if you've got a little, piece of metal like that, and you tick it, it will tend to sort of have this kind of situation. If you have a drum and you hit the drum head, the drum will sort of go, the drum head will go like wah, 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 but it'll also go like wah, 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 like that, and then the other way it's going to go wah. There's like multiple integer harmonics. So everything does that in the world. And so so if you take a clarinet or a flute or your voice and you just go, and then record that with an oscilloscope, what is it? Oh, it's one last thing. These are, all at the same time. So this is kind of an abstract way, all at, same time. Add them all up. So you can have different amounts, different proportions of each harmonic. So you might have a lot of second harmonic or a lot of fourth harmonic or third harmonic. And that's what makes the sound like it is. And so they call that, timbre. A lot of times, a French word, which they pronounce in English timbre usually. That's the quality of the sound. But what does it look like if we plot it out just on a simple graph? So it just looks like if this is, time going this way, and we just take a clarinet and just go, just play a particular note. Well, what you see is there'll be the first harmonic. That's the first. And then there'll be, whatever that is. If that was 100, then there'll be 200 and 300 and 400, 500, 600. Different amounts of those. So what Helmholtz did is he found that, and so any sound that has multiple frequencies in it is going to look like that. Now, how can you get a single frequency? Like if you take a tuning fork is just like a piece of metal that sort of looks like this. And that, if you ding that, it will tend to make a pretty pure tone. Not perfect, but depending on what you hit it with. If you hit it with a nice little rubber mallet, you can get, a pure single frequency. In the days, before computers. And so what Helmholtz did is he just said, let's say this was just 100 hertz. So 100, 200, 300, 400, 500, 600. So if you just play all of those, you get tuning forks, for 100, 200, 300, 400, 500, 600, and ding them all at the same time. It sounds like 100. And depending on how much of the fourth and the fifth and the sixth harmonic you have in there, it will change the color of the tone. So it might change it from something like, to something like ooh. Those are different amounts of these different higher harmonics. But that pitch sounds like the first harmonic. So then he just did an experiment. Helmholtz did this. Let's ding the second, third, fourth, fifth, and sixth harmonic, and leave out the first. So if you ding a 200, 300, 400, 500, 600 tuning fork and leave out the 100, it sounds exactly like 100, even though there's no 100 in there at all. And so, that's the missing fundamental. That's, if you want to read about it, like it's the quote unquote illusion of the missing fundamental. And so that suggests that your system kind of knows about this. And it's not just a quick example, like, what about a flute? So a flute is like it's like a tube with both ends open. And so when you blow into a flute, what happens, you get harmonics from the flute also. And it's a little more complicated. This represents the actual pressure inside the flute. So the pressure has to be atmospheric pressure at the outside of the flute, but the pressure can be higher in the middle of the flute. That's in the middle of the tube. So here's this is the tube. So that would be the first harmonic. And so the pressure is going sort of negative and positive. And, in order to make a pressure wave, you have to move some of the atoms. And so the atoms are moving like this. So they move the most. They actually move the least where the pressure is the highest. So this guy is pressure, and this other one is movement. So that's the first harmonic of a flute, and that will sort of go. The movement is going back and forth also, but you could have a second harmonic, and it's pretty much the same as the guitar. So what will happen is you'll have the second harmonic, can go like this. And so in that case, the pressure is 0 in the middle of the flute, and it's higher off to the sides. And so that you got the same thing. You got the same thing in a clarinet. A clarinet is similar, but it's got a sealed end, and so the pitch of a clarinet is lower. If you take a flute and put a clarinet mouthpiece on it and blow it, it sounds like a clarinet. It goes down an octave and it sounds like a clarinet because it's got a sealed end. And you could put if you could open up a hole at the top of a clarinet and put a flute mouthpiece on there, and then suddenly the pitch will be higher. That's actually the way the octave key works. It opens up a hole. So there's a lot of complicated things. But the bottom line is there's a whole bunch of stuff out there, and it always does that. It just does this. It does this multiple integer frequencies. That's kind of everything. Any kind of physical object is going to vibrate with some combination of these harmonics. And so your system is not stupid. It's listened to a lot of stuff. And so let's look at, so what's actually going on. So if you look in auditory cortex, so here's like a big picture of, A1. So we've got, frequency going this way. So what does it look like if I go and look in the auditory cortex? What's actually in there? Well, what's going to be in there is there's going to be, it's a point to plane, so there's going to be the fundamental frequency. That might be, say, 100 at the 100 hertz part of the map. Then there's going to be 200 in there. But now we've got to deal with the fact that the representation in there is approximately, it represents frequencies exponentially, but it's kind of like you can think of the inverse of that, which is a log. So as you go to higher frequencies, to move the same distance in cortex, you've got to increase your frequency a lot. So, and this kind of reflects the way sounds sound. So if I go, that's an octave, that's twice the frequency. Then if I go, that's 4 times the frequency, even though it sort of sounds, those sound approximately the same distance apart from each other, but that's actually like 100, 200, and 400. And so when you look at the map in here is kind of logarithmic, so the frequencies compress as you go up. And so what's going to happen is, the next frequency, if you look at where 300 is in the map, it's closer like that. So that's where 300 is in the map. And whereas, 400 in the map is even closer. And what about, 500? That's even closer. And so that's actually what, and then there's 600 and 700. So it all sort of like piles into the same place when we get to the top. So that's basically what an actual sound looks like in auditory cortex. And so when we hear this pitch, this very clear pitch of, it sounds like a single pitch, you can find it on the piano, that just corresponds to this guy. So what is pitch? Pitch means let's take this whole mess in and then conclude, that's the actual pitch. So your system is constantly getting stuff like this. Now, how would another pitch look? Well, that's going to be complicated. So maybe there was, a pitch here, right? And there's going to be twice that frequency, and then, a logarithmic sort of getting closer and closer thing going on. So this is another pitch. They might be on at the same time. You can easily hear, so if you put 2 pitches on, you can, if they're far enough apart, you can hear them. And so that guy, is going to, we're going to have to listen to those and figure out, it means that pitch. It means that pitch. So that's actually what sounds actually look like in the system. And why, what causes this? So people have come up with various theories for what causes it. Is it something that's some physical thing about how the cochlear membrane vibrates? Maybe that is kind of, maybe the basilar membrane has some harmonics in it. But the bottom line, we're getting very close. I'll stop in 30 seconds. So the bottom line is they did this great experiment with mice. So they played mice sounds that contained harmonics that weren't integer multiples. And then they tested whether neurons became sensitive to missing fundamentals with these kinds of weird stimuli. And it turns out the mice learned non-integer fundamentals. Okay, so I think I'll end there before the recording goes into the next thing. So the bottom line is they probably just learn it. You just learn it by listening to drums and clarinets and everything like that. Okay. Okay, so any questions about pitch, or what about the clarinet or the flute? All good on pitches. I've often, people talk about perfect pitch, how you can sort of like identify a note that you hear, but they don't talk about perfect retina. Perfect retina would be somebody shows you, here's your visual field, and they show you a spot right there in your visual field. And what perfect retina is you would say, that's 45 degrees polar angle and 17 degrees eccentricity. So, whereas perfect pitch, you play this sound with harmonics in it, and then you're able to say, like, yeah, I know that's the C on the second string of a guitar. Okay, Stan. Did I go over too much? It was okay.